This video is going to look at a special case of factoring, and that is factoring a difference of perfect squares. When we discussed multiplying polynomials, we learned one kind of special pattern. If you multiply a plus b times a minus b, the inner and the outer terms cancel out and you're left with a squared minus b squared. So in the context of factoring, that means if we see something of the form a squared minus b squared, we can factor that as a plus b, a minus b. So here's an example. Factor y squared minus 9. This is a difference of perfect squares. We have y squared minus 3 squared. So using our pattern, we can factor this as y plus 3, y minus 3. If we wanted to check our work, we could FOIL this out, and we will get what we started with. 25c squared minus 4. Two terms, it's a difference, and they're both perfect squares. 25 is the same as 5 squared, so that 25c squared can be written as the quantity 5c squared. 4 is 2 squared. So this can be factored as 5c plus 2, 5c minus 2. 18x squared minus 32. Two terms, and we have a difference. However, 18 is not a perfect square. Neither is 32. But in the last video when we talked about factoring, we learned that the first thing we should do in a factoring problem is really check and see if there's a GCF, or greatest common factor. So do we have a GCF? Well, 18 and 32 are both even numbers. They're both divisible by 2. So I can actually pull that GCF of 2 out front first, and if I take the 2 out, I'm left with 9x squared minus 16. And now let's check. Are these perfect squares? Yeah, 9 is 3 squared, 16 is 4 squared. So 9x squared would be the quantity 3x quantity squared minus 4 squared. So I can use my pattern. The GCF is going to stay there. And then the 9x squared minus 16 turns into 3x minus 4, 3x plus 4. Notice the order you put the plus and the minus doesn't matter. I could have written this as 3x plus 4 and then 3x minus 4. Again, the order of the plus and minus doesn't matter in these problems. So there's my final answer. 2 times 3x minus 4, 3x plus 4. Here's one more example. I've got 5z squared plus 20. So the first thing I should do is look for a GCF. Is there something we can divide both terms by? Yeah, both terms are divisible by 5. If we take the 5 out front, we are left with z squared plus 4. Now, is this a difference of perfect squares? 4 is a perfect square, but notice we don't have that minus sign. That's important. Our pattern only works for subtraction, a difference of perfect squares. And so when you have a sum of squares like this, z squared plus 4, this cannot be factored any further. And my final answer is 5z squared plus 4. We just can't go any further with this one. All right, that was my last example. As always, please let me know if anything is unclear in this video.